Okay. Good morning, everyone. Let's continue with the root locus. Okay. So let us consider problem number 2. Okay. Given that open loop transfer function g of s into h of s is k divided by s into s plus 3 into s square plus 2s plus 2. Okay. Now, if possible, not everyone, whosoever can, they can buy graph sheets. Okay. So whatever problems I'm going to discuss in the class, I want you to practice in a graph sheet. Okay. So in your graph sheet, probably you can take the scale as x and y scale. Something like 2 units is equal to 1 centimeter. Okay. So that means to say along x-axis you take 2 units as 1 centimeter, and also along y-axis you consider 2 units as 1 centimeter. Okay, always you have to take uniform scale, or else you will get kind of non-uniform graph. Okay. Select 1:1 scale. Okay. Fine. So this is the problem. Okay. Now, if you look at the problem very closely, you have a quadratic function here, and what you have to do is, let's jump into the solution. So rule 1. So you need to construct the root locus for k from k variation from 0 to infinity. So k is varied from 0 to infinity, and for this variation you need to construct the root locus. So let's start rule 1. So root locus is symmetrical with respect to real axis. Okay. So that's your rule 1. Rule 2, let us identify the poles and zeros. So let us call P is equal to open loop poles. And how many open loop poles do you have? 4, right? 1, 2, and 2 roots. So totally you have 4 open loop poles, and they are 0, -3, and find the roots of this particular equation. The roots of s square plus 2s plus 2 will give you -1 plus j1 as the first root, and the second root going to be the conjugate value, -1 minus j1. So one root, second root, third root, and fourth root. Okay, so that's about P. Next you have open loop zeros. How many open loop zeros? No. 0 open loops. Right. So the terminating points are basically infinity, infinity, infinity. That's because you don't have any open loop zeros. Yeah. So zeros are nothing but terminating points. Correct. And poles are nothing but starting points. All right. Done. Next, you can compare, say for example, P with Z. So P count is 4, Z count is 0. So P is greater than Z. That implies N is equal to P is equal to 4. And what is N? Root locus branches, RL branches. Okay. Since pole count is greater than 0 count, P minus Z branches, that is equal to 4 minus 0 is equal to 4 branches move towards infinity. Since you don't have any finite zeros in your transfer function, what is happening is p minus z branches, so that is 4 minus 0 is 4. You can say that all the 4 branches are moving towards infinity. Okay, so other day, the problem what we solved had 2 finite open loop zeros. So due to which what happened? The root locus branches got terminated at those 2 zeros. But in this problem, we don't have any zeros. So you would see that eventually that all the branches will move towards infinity. So since we are saying all the branches are moving towards infinity, you must get asymptotes as well as centroid for this problem. Let us see. Okay, so that is rule 2. Rule 3. Okay, what is rule 3? Rule 3 is about existence of root locus on real axis. Existence of root locus on real axis. For rule 3, what you have to do? You have to construct the pole 0 plot. Okay. Real axis, the negative real axis, minus infinity, that is considered. And here you have plus j omega, and here you have minus j omega. So quickly let us draw the pole 0 plot. You don't have any zeros, so no need to draw. Only you have to place the poles. Pole is present at origin, and one more pole is present at minus 3. Okay. And the 2 poles are basically complex conjugate. So they don't occupy along the real axis. Instead, they occupy the 2-dimensional plane, right? So real part is minus 1. So let's say this is minus 1. And imaginary part is plus or minus j1. So probably here you can mention. First root, second root, third root, and the fourth root. Okay. Once you are done with the pole 0 plot, what you have to do is you have to select the imaginary or sections on the real axis. So you have a pole at origin. So to the right hand side of this pole, you draw a section and mark this section as 1. What about these 2? You cannot consider because existence of root locus on real axis. For this, what you have to do is you have to consider only real poles and zeros. Do not consider complex conjugate poles or zeros. So you have a real pole at origin and you have a real pole at minus 3. So the next section is drawn closer to minus 3. So this is your section 2. Now I'm not going to consider these 2 poles because they are complex conjugate, because the real part is not on the real axis. It is found in the 2-dimensional plane, correct? And finally, as a boundary condition, you consider the third plane, which is found closer to the negative infinity. Okay. And now you count how many poles and zeros are present on the right hand side. Okay. So covering the first pole, let us count how many zeros are present on right hand side of section 1. How many? None, right? So it's a 0 count. 0 is a even number. Hence, entire positive real axis is NRL. No root locus. You cannot have any root locus along the positive real axis. Next, we have a real root at minus 3. So cover this minus 3 and count how many poles and zeros are lying on the real axis. Only 1, right? So 1 is a odd number. So between 0 and minus 3, there exists a root locus. So what we can do is we can draw a thick line. So thick line indicates that there exists a root locus. So thick line indicates that there is root locus between 0 and -3. Okay. Done. Finally, you can go to the boundary condition, which is at -infinity. Okay. So taking section 3 as your final section, count the number of poles and zeros. You will find that 2 poles are present. So 2 is an even number. So between -3 and -infinity, you can say that there is no root locus. So you can write NRL. So only the valid root locus region is between 0 and -3. Okay. So that is the takeaway, what you get from rule number 3. So once you are done with rule 3, you can go to rule 4. Okay. What is rule 4? The sigma or the centroid calculation. Rule 4 is centroid, sigma, which is also called as the merging point of asymptotes. And how are we going to find sigma? Sigma is calculated using the following formula. Sigma is equal to summation of real part of poles minus summation of real part of zeros divided by p minus z. So that is equal to real part of poles. So when you say real part of poles, you have to consider all the poles. It could be real poles or it could be complex conjugate poles. Okay. So you have poles at 0, -3, and -1 plus or minus j. When you consider the poles, you have to consider only the real part of those poles as well as real part of those zeros. Okay. So can you tell me real part of poles? 0 and then -3, then -1, -1. Okay. Why am I writing 2 times -1, -1? Because I have a complex conjugate pole whose value is -1. Here I write my complex conjugate poles. 2 are real, 0, -3, and 2 are complex conjugate, -1 plus j1 and -1 minus j1. And the real part of these 2 poles is -1. So I have written -1, -1. Okay. Minus real part of zeros. As you can clearly observe, you don't have any factors in the numerator, hence this part is 0. Divided by p minus z. P is pole count, which is 4, and z is 0 count, which is 0. So what do you have? You have -1, -1, -1. Correct. -3, -1, -1. So -5/4. So sigma is -5/4. So that is -1.2. So -1.2 is our centroid. 2.5. -1.25 is the centroid. All right. So once the centroid is found, you can find the angle of asymptotes. Again, formula driven. Angle of asymptotes can be found as theta is equal to 2q plus 1 into 180 degree divided by p minus z, where q is equal to 0, 1, so on and so forth until p minus z minus 1 is found. Okay. So what is p minus z minus 1? P is 4, z is 0, and -1. So 4 minus 1 will give you the number as q. So q value is 0, 1, 2, 3. So q has four values, 0, 1, 2, 3. So taking these values independently, you are supposed to find the angle of asymptotes. Okay, so let's find it. So when Q is equal to 0, so when you set the value of Q as 0, let us say the angle, corresponding angle is theta 1. So theta 1 is what? 2 into 0 plus 1. So basically you have 180 degree divided by P minus Z. P minus Z is 4, right? 4. So that is 45 degree. So the first line or the asymptote you must draw with an angle of 45 degree starting from the centroid, which is located at minus 1.25. And when you set Q is equal to 1, you will get the second angle of asymptote, which is, okay, when you set it 1, what will happen? 2 into 1, that is 2 plus 1. So basically it is 3 into 180 by 4. Okay, so that's 135 degrees. Okay, 3 times the first angle. And when you set it Q equal to 2, you will get the third angle, theta 3. And theta 3 is what? 2 into 2 plus 1. So 5 times. 5 into 180 by 4. So basically, it is the odd multiples of theta 1. Correct? 45 into 3, 135 into 5 is 225. Similarly, the last angle, theta 4. So theta 4 is for Q is equal to 3. So 2 into 3 is 6. 6 plus 1 is 7. So 7 times 180 by 4. How much is it? 315? Is it 315? What do you get? Yeah, 315 degrees. So theta 4 is 315 degrees. Okay. So first let us collect all the values, and in the end we can draw the root locus. Okay. So theta 1, theta 2, theta 3, theta 4 is found along with the centroid. Okay. So basically what you have to do is, in your root locus, you have to first locate the centroid, which is at minus 1.25. This is at minus 1.25. Now, taking this centroid as reference, you have to draw the straight line having the following angles. So first of all, you have a straight line with 45 degree angle. 45 degree. And next you have a straight line with 135 degree angle. So this is 135 degree. And next you have 225 degree. It could be the extension of 45 degree. So this is, okay, I'll write it theta 3. Okay, this is theta 2. And this is theta 1. And finally, you have 315 degrees. This time, theta 4. So this is draw them using thin lines, okay, because these are not the part of root locus. They are just the guidelines, so meant for helping us to construct the root locus. All right. So that is about rule 5. Rule 6, what is it? Breakaway point, I guess. Rule 6, you can write breakaway point. Breakaway points. Okay. So to find breakaway points, you must find out first of all the characteristic equation f of s. So f of s is 1 plus g of s into h of s. That is 1 plus k divided by s into s plus 3 into s squared 2s plus 2 is equal to 0. So simplify this. Okay. This is s squared plus 3s into s squared plus 2s plus 2. Okay. So when you simplify, you will get a fourth order equation. So you will get characteristic equation f of s is equal to s to the power 4 plus 5s cubed plus 8s squared plus 6s plus k is equal to 0. This is your characteristic equation. You can cross check later. Let us mark this characteristic equation, okay? Because we need this characteristic equation for root table as well. Okay. So once you have the characteristic equation, let us find k. So k is equal to what? Any of this is 0. So k is equal to, you can take all the s terms onto the right hand side. So negative s to the power 4 plus 5s cubed plus 8s squared plus 6s. So k is equal to this. So what you have done is you have taken all the s terms onto the right hand side. So once you have k, in order to find the breakaway points, dk by ds. Okay, in bracket, let me write this dk by ds is also called as root sensitivity. Dk by ds is nothing but root sensitivity and other words. So differentiate and equate it to 0. So when you equate it to 0, you will get the roots of dk by ds, which are nothing but the breakaway points. So let's differentiate. So minus 3s cubed plus 15s squared plus 16s plus 6 is equal to 0, or you have 3s cubed 15s squared 16s plus 6 is equal to 0. Okay. So basically when you differentiate, fourth order equation becomes a third order equation. And when you solve this particular third order equation, you will get S1, 2, 3 as the breakaway points. And when you solve this particular equation, okay, I'm sorry, 4s cubed, right? This should be 4s cubed. This is 4s plus 15s squared plus 16s squared. So when you solve, you will get the roots as minus 2.3, comma, complex conjugate roots you will get. Okay, the remaining roots as minus 0.725 plus or minus j 0.365. 0.365. So two roots, right? Minus 0.725 plus j 0.365 minus 0.725 minus j 0.365. Validate these roots using rule number 3. You have to check whether all these are valid breakaway points or not. Okay, can anyone quickly validate? Okay, what about this minus 2.3? Is it a valid breakaway point? Quickly, you go to your rule 3, wherein you have identified the valid and invalid root locus sections. 0, minus 3, plus or minus j1. And rule 3 is applicable only for real rows, as in, okay, let me come to it. So this is your NRL, right? And between 0 and minus 3, you have RL section. You have RL section. Okay. Now, the first root is minus 2.2, and minus 2.3 is somewhere here, it is getting placed. Let me call this as breakaway point 1, which is equal to minus 2.3, which is a real root. Now, if you look at the placement of the breakaway point, you are observing that this particular breakaway point is getting placed in RL section. So this is RL section, right? Because between 0 and 3, we have predicted that there is a root locus. So you can say that the first root, that is negative 2.3, is a valid because it is getting placed in the valid sections of, valid section in the root locus, right? Fine. Very simple whenever you get real root. Now you come to this complex conjugate. Can you say this is valid breakaway point? Can you say this valid breakaway point? No, we can't say. We don't know whether it is valid or invalid. That's because rule 3 is applicable to only real roots. Remember, rule 3 is applicable to only real breakaway point. Very, very important. Very, very important. Okay. If it is applicable to only real breakaway point, then how are we going to check the validity? You remember in the introduction class, I was explaining about the angle condition and magnitude condition. What is the significance of angle condition? If a test point has to be there on the root locus, then it must satisfy the angle condition. So the validity of this particular test point can be checked using the angle condition. All right. So just below this, probably you can write a note that the validity of complex conjugate, breakaway point is done on the basis of angle condition. On the basis of angle condition. Okay, very, very important. All right, so let's apply the angle condition. So whenever you get complex root, it is something like, suffocating, because it becomes very lengthy. The root locus problem becomes very lengthy. So that's the reason, I've been telling you to practice. Okay, this is only the second problem. Doesn't matter. Probably after this problem, you please practice. Okay, such problems. Now, angle condition. What does the angle condition say? The angle condition says that angle of g of s into h of s at any test point yes should be equal to plus or minus 180 degree into 2q plus 1. Okay. And what is q? We have already formed, right? So q is equal to p minus z minus 1, right? So it is 0, 1, 2, 3. So it is basically plus or minus 180 degree. You can find out plus or minus 180 degree or comma When you set q equal to 1, you will get 3. So 3 times 180 is plus or minus 540 degree, and then 5 times 180 is 900 degree, and then 7 times 180 is plus or minus 126 degrees. So basically, you have a circle, right? Circle is 360 degree rotation. So you will have multiple rotations, okay, 2 rotations, 3 rotations, etc., etc. Okay, because as such, you cannot just draw a straight line and draw a line having 1260 degree inclination, right? You have to do several rotations. All right. Now, what I'm trying to tell you over here is that when you substitute the test point value in your transfer function, the ultimate angle what your transfer function gives should be one of these. Either it should be plus or minus 180 degree or plus or minus 540 degree. If you get an angle, which is equal to say these angles, you can say that the 2 breakaway points are valid because it satisfies the angle condition. If you don't get these angles, then you can simply say that the breakaway points are invalid. So out of 3 breakaway points, only 1 breakaway point is valid. So that's what you can conclude. Okay, quickly let us do it. So for that, I need to have the open loop transfer function. Hopefully, the open loop transfer function is ready with you. Okay, so let me factorize the system first. So I can say g of s into h of s. And say one step directly. I can say at point s is equal to, okay, what is that breakaway point? Minus 0.725 plus j 0.365. Okay, minus you need not take because the second point is basically the mirror image of, let's say, these are the 2 complex points. So point B is nothing but the mirror image of point A. So point A, if it gives, let's say, 60 degree angle, point B should give you minus 60 degree angle because it's a mirror image, right? So only one route you can consider while checking the breakaway point. So that is equal to, okay, in the numerator, what do you have? Angle of K. So what is angle of K? Is 0 degree because K is real number. Okay. Divided by, okay, angle of S, you have a factor S there. So S needs to be replaced with minus 0.725 plus J 0.365. Okay. Plus, because angles are added, correct? Plus, what do you have the second factor in your denominator? S plus 3, correct? S plus 3 you have. So against S, you substitute minus 0.725 plus J 0.365. Okay. I erase this. Hope you have copied. Plus 3. Plus 3. Plus, you have the quadratic equation s square plus 2s plus 2. Okay, the roots of the quadratic equation are basically, okay, roots of s square plus 2s plus 2 can be written in a factored manner as s plus 1 minus j1 into s into s plus 1 plus j1, right? Because when you equate it to 0, what is the root value of the first factor? S is equal to minus 1 plus j1. When you equate the second factor to 0, what do you get the root value as? S is equal to -1 minus j1. Okay. So that you can carry out the addition very quickly. So against S, you substitute -0.725 minus 0.725 plus j 0.365 plus 1 plus j1 plus 1 minus j1 plus angle of the second root, that is minus 0.725 plus j 0.365 plus 1 plus j1. Okay. Done. So after writing down the value of S in the transfer function, what you have to do is you have to use your calculator. Okay. So use calculator in polar notation. In polar mode. Okay. Don't use tan inverse of y by x formula, because I'm again repeating, the calculator is programmed to measure the tan angle between 0 to 90 degrees. That means to say it handles angles only in one quadrant. So tan inverse of y by x, if you do, what happens is that it fails to address these problems. Okay, if your point is located in the second quadrant, okay, if your point is located in second quadrant, the angle becomes greater than 90 degrees. So tan inverse formula cannot be used in such situations. So in such situations, what you can do is you can use polar mode. So polar mode, in order to use, you have to set your calculator to comp mode. Okay, that is mode, the first key switch you have to do. Okay, first key switch you have to do. Forget it. Comp mode you have to use, and use shift button and use number 2. Okay, number 2 you use, because under number 2, sorry, not number 2, plus sign. Under plus sign you have a polar mode. Okay, so substitute in polar notation, that is polar of, this is the syntax, real part, comma, imaginary part. So when you substitute real part, comma, imaginary part, for example, let me consider the first number. So what I will do, shift pole of minus 0.725, shift comma 0.365 is equal to, I get my r at an angle theta form as something like 0.8116 at an angle 153.27. So the angle, I do not want magnitude because I'm not satisfying magnitude condition. I'm trying to validate the angle condition. So what I'll do, I'll just collect the angular part. So angle for the first complex number is theta is equal to 153.27 degrees. Okay. So similarly, you try finding out the angles of remaining complex numbers. So angle of g of s into h of s, you will get it as 0 degree divided by the first angle I have already shown you, 153.27 degree. Okay, the remaining angle, I will write it down on the board. You can check probably later. Okay, so you will get plus 9.11 degree plus 78.6 degree minus 66.58 degree. 5 degree. Okay, and you get the net angle of the transfer function at s is equal to 0.725 plus j 0.365 as 0 degree minus the bottom angle, right? So minus 174.4 degrees. So what is your net angle? Minus 174.4 degrees. Now, is it satisfying the angle condition? To satisfy angle condition, you should have got at least plus or minus 180 degree. So this is not equal to plus or minus 180 degree. Hence, you can conclude that this is not a valid breakaway point. This is not a valid breakaway point. All right. Tedious, right? It is tedious, but you have to spend some time in order to get the speed. So this is not the breakaway point. Okay. If this is not the breakaway point, obviously his twin brother cannot be the breakaway point. Okay, so both are invalid breakaway points. So this particular problem is having only one breakaway point, which is a real breakaway point, and which is located at minus 2.3. Okay. Next we have rule 7, intersection with j omega axis. Intersection with j omega axis. Now for this you must have the characteristic equation. So characteristic equation f of s is equal to, we have already written, right? Characteristic equation, it is s to the power 4 plus 5s cubed plus 8s squared plus 6s plus 4 is equal to 0. So that's your characteristic equation. So what you can do is you can quickly construct RH table. RH table S4, S3, S2, S1, S0, 1, 8, 4. Okay, this is K, right? This is K. Six S plus K, right? And 5 and 6, and this is 0. So what do we have? 40 minus 6, right? 5 into 8, 40. 40 minus 6 is 34. 34 divided by 5, 6.8. 6.8. And this is 5k minus 0. Divided by 5, that will give me k. Okay. And the second one is 6.8 into 6 minus 5k. $40.8 minus 5k divided by 6.8, 0, and here you will get k. And from the RS table, you can say that for stability, okay, you would want your first column entries to have the same sign. So it is starting from +1. So all first column entries should have the positive sign. So starting from s to the power 0 row, you can say that k should be greater than 0. Right? So next up we have s to the power 1 row. So from s to the power 1 row, you can say that 40.8 minus 5k divided by 6.8 should be greater than 0. Or 40.8 minus 5k should be greater than 0. Or k should be less than 40.8 divided by 5. Or 40.8 by 5, you will get it as 8.16. 8.16. So for stability, the range of K should be greater than 0, less than 8.16. Once you get the range of K, you can find out the marginal value of K. Okay. Now, for getting marginal value of K, when you substitute a K value, you should get a row of 0. So I see only one possibility here. That is s to the power 1 row. So this is susceptible for row of zeros, right? Because one element is already 0. So when you substitute the root of this first term, you will get row of zeros. That is 8.16. So when you substitute K equal to 8.16, this entire function becomes 0 because 8.16 is basically root of this particular function, right? So 40.8 minus 5 into 8.16 is 40.8. So 40.8 minus 40.8 is 0. So you'll get a row of zeros. Row of zeros. And to get row of zeros, what should be the value of K? K marginal is 8.6. So I can erase this, right? This is done, right? So K marginal is 8.16, which is a positive number. So K marginal is 8.16 and it is positive. Therefore, the root locus intersects with j omega x. So whenever you get positive value of K marginal, you would say root locus intersects. If you get negative value of K marginal in the previous problem, right, problem number 1, you can say that root locus never intersects with j omega axis. So if it intersects, what are the intersection points? What are the intersection points? So to find the intersection points, what you have to do is you have to create an auxiliary equation from a row which is sitting above the row of zeros, that is s square row. So let's create the auxiliary equation A of s. So A of s is equal to 6.8 s square plus k. What is k? K marginal is equal to 0. So 6.8 s square plus k marginal 8.16 is equal to 0. So 6.8 square minus, is equal to minus 8.16, or s square is equal to minus 8.16 divided by 6.8. S square is equal to minus 8.16 divided by 6.8. That implies s square. So what are the roots? S1 and S2. So S1, 2 is equal to, is it too congested? Nevertheless, let me write it here. We got s square as minus 8.16 divided by 6.8, which is minus. Okay, let's take the ratio. 8.16 divided by 6.8 is 1/2. Is minus 1/2. Or yes, 1, 2 is equal to plus or minus under root minus 1.2. Or this can be taken as is equal to plus or minus. You can actually under root minus 1 into under root 1.2, right? Is equal to, what is under root minus 1 in complex notation? J. So plus or minus j into under root 1.2. So under root 1.2 is 1.095. So the imaginary roots are plus or minus j 1.095. Therefore, at k equal to 8.16, the root locus intersects at plus or minus j 1.095. So your root locus will cut at plus or minus j 1.095. Okay. So that's about rule 7. So in rule 7, majorly you need to calculate k marginal and range of k greater than 0, less than 8.16, and the crossover points. So the three important aspects for root locus are found in rule 7. Finally, you have rule 8. What is rule 8? Angle of departure and angle of arrival. Now, in the previous class, I had mentioned about when to calculate angle of arrival and angle of departure. So, if your transfer function is having a complex conjugate pole or 0, you need to find out angle of arrival or angle of departure. Now, in the given problem, you have a complex conjugate pole, right? That is -1 plus or minus j1. Hence, you need to apply rule 8. So, using rule 8, you need to find angle of departure. Why departure? Because you have a complex conjugate pole. So for pole, it is departure, and if you have a complex conjugate 0, you need to estimate angle of arrival. Now, very simple to calculate the angle of departure. So angle of departure is calculated using the formula phi d is equal to 180 degree minus phi. Okay, where phi is equal to summation phi b minus phi z. It's in the formula what we use. Now, what is phi b and what is phi z? That we need to find. To find phi b and phi z, okay, phi b and phi z are found from the pole 0 plot. From the pole 0 plot. So to find phi b and phi z, in other words, to find phi d, you need to draw the pole 0 plot. So quickly let us draw the pole 0 plot. One pole at origin, one pole at -3, and two complex conjugate poles. Right? I mean, pair of complex conjugate poles. J1 minus J1, and this value is -1. So let us say this is complex pole A, and let us say this is complex pole B. Okay, listen carefully. Now, phi p is nothing but the net angles measured from each of the poles connected to the complex pole under consideration. Net angle connected to the complex pole under consideration. What do you mean by that? Now, to calculate phi d, what you have to do is you have to first identify your complex pole. You have two complex poles. One is found in second quadrant and the other is found in third quadrant. So phi d needs to be calculated only once, because whatever phi d you get for point A can be written for point B with a reverse sign. That's because point B is mirror image of point A. Correct. Point B is mirror image of point A. So let us write. Here it is. Point D at point A is equal to. What you have to do is, in order to find phi p, you have to connect all the poles and zeros to the pole complex pole under consideration, right? What do you mean by that? I have a pole at origin, right? So what I will do, using a scale, okay, so that's the reason, because you are doing angle measurement, it needs to be very, very accurate. So you have to do it in a graph shape. So connect the pole at origin with the pole under consideration. All right, and measure the angle. So this angle, you let's say call it as phi p1. Done. Next, you have a pole at -3. So connect this pole with the pole under consideration. Okay. And once again, you measure the angle. Let us say this angle is phi p2. And finally, you have the third pole, right, which is his twin brother, right? So you measure this angle as well. So this angle is pretty simple, right? Phi p3, which is 90 degrees. So these are your phi p's. Now, phi z is nothing but the angle made by a zero. Now, in our transfer function, we never had any zero. If you, let's say, if you were to have a zero somewhere here, what you would have done, you would have connected that, let's say, some zero is present at +1. And what you would have done, you would have connected this zero to this pole under consideration. If you connect a zero to the complex pole, the resultant angle is taken as phi z. So this phi z are nothing but the angles made by finite zeros with respect to the complex pole under consideration. All right. I'll erase this because you shouldn't be in a wrong notion that there is a zero in your transfer function. So once you have this, you can measure phi p, phi 2, phi p3. So phi p1, phi p1. Okay, I have measured. You can try out phi p1. You will get it as 135 degrees. Okay, you can just place your protractor to measure the angles. And phi p2, you will get it at something like 26.6 degrees. Okay, and phi p3, pretty simple, right? Always the conjugate pole will give an angle of 90 degrees. 90 degrees. Okay. So phi d is calculated as 180 degrees minus phi. What is phi? Phi p minus phi z. So there is no phi z. So phi z is 0 degree for the given system. So it is 180 degree minus 135 degree minus 26.6 degree minus 90 degree. So you would get phi d at point A as 71.6 degrees. Okay, roughly 72 degree. Okay, say 72 degree. 72 degree minus 72 degree. Now, the departure angle is minus 72 degree. So what is the departure angle at point B? It is plus 72 degree. So this angle of departure needs to be calculated only once. Once you get the angle of departure value for the mirror image, you can simply reverse the sign. Okay. So this is what the angle of departure calculation is all about. Okay. Now, I want you to write a note. Okay. So what happens is that at angle of departure, root locus branch moves tangentially. at angle of departure, root locus branch moves tangentially with respect to phi d with respect to phi d length. These are all standard results. Okay? So you need to know about all this. This is an important point. Okay. So that completes the calculation part of root locus. So next we have the construction part. Construction part. Do construction part. So I want you to, go through the rules. What did we do in rule 1 and what did we do in rule 8? I want you to go through. Once this is done, I can go ahead with the root locus construction. Okay. I would be needing 10 minutes of your time to complete the plot. Okay. So please excuse me for 10 minutes. Okay. So let's plot the root locus. Minus sigma plus sigma plus j omega minus j omega. Draw the linear scale along x and y axis. Okay. Done. So that is mark the points plus 1, plus 2, plus 3, plus 4, and minus 1, minus 2, minus 3, minus 4, J1, J2, J3, minus J1, minus J2, minus J. So what I have done is I have taken scale. I have taken x-axis and y-axis, something like 1 unit. Okay, I've taken 1. Taken 3 units. Taken 3 units as 1 centimeter. Three units as 1 centimeter. Yeah. So this is your complex plane. Okay. Now you place the poles and zeros. You have a pole at origin. and then you have a pole at -3. Okay, and then you have a complex conjugate pole at -1 plus or minus j omega. J omega. Okay. Let's say this is your point A, and let's say this is your point B. Right? You want, right, those points because you have to draw the angle of departure at point A and point B. Okay. Once this is done, you can place the centroid. Okay. The centroid was -1.25. Okay, -1.25. Okay, here. Sigma is -1.25. So taking the centroid as the reference, we have to draw a straight line. So 45-degree angle you have to draw. So something like this, you will get 45-degree angle. Theta 1 is equal to 45 degree. Theta 2 is equal to 135 degree. Theta 3 is 225 degree. And theta 4 350 degrees. Okay. So what we have done is we have drawn the angle of asymptote. So always you can draw with dotted lines. Because as I said in the beginning, they are not the part of root locus, they are just the guidelines. Okay, they will help us in constructing the root locus. You can draw with dotted lines. Okay. So those are your angle of asymptotes. Okay. All right. So once asymptotes you have drawn, what you can do is you can now start locating the breakaway point. So where is your breakaway point? The breakaway point is found at -2.3. Okay. And also you please mark the valid root locus section. What I will do, this is your valid root locus section. Okay. If you have any confusion, what you can do, you can refer rule number 3. Okay. So it is at -2.3. So -2.3 is somewhere here. Somewhere here. Breakaway point, which is at -2.3. The breakaway point. Done. Now let us construct the root locus. How do we construct? First, let us, pay our attention to the roots which are located on the real axis. So you have one root located at 0 and the other root located at -3. So as the value of k is varying, what will happen is these two roots, they start to move. So consider first this. Now the question is, can this root move along positive real axis? No, because positive real axis is NRL for us. So no root locus. We have already did the prediction in rule number 3. So the root cannot move along positive real axis. That means to say the root needs to move along the negative real axis. So this root will move like this, and here it comes. Look at the arrow direction. So the arrow direction simply says that this root is left-hand side, left-hand side bound. Okay, fine. And what about the root which is found at -3? Can it move along negative real axis? No, it cannot move in the left-hand side direction. That's because from -3 you have another. So it cannot move in the left-hand direction. So in which direction it should move? Only in the right-hand direction. Because between -3 and 0, you have the valid root locus, right? So this root is going to move in this direction. So the two roots are meeting at this particular breakaway point, which is located at -2.3. So once they meet at this breakaway point, what will happen? They will break away. They will move away. Now, when you say move away, in which direction it should move? You remember rule 2. We had predicted that out of Z branches, all the 4 branches are moving towards infinity. So what happens is that once they break away, the upper branch will move along the nearest asymptote. So where is the nearest asymptote? Nearest asymptote for the upper branch is θ2. So what will happen? The first branch will move parallel to θ2, and the second branch will move parallel to θ3. This is how the root locus will move. And where do they go? They move towards infinity because there are no terminating points. So these two branches, they simply move towards infinity. So fine. You had p is equal to 4. Out of 4 roots, you have projected 2 roots towards infinity, with respect to the nearest asymptotes. Okay, what about the remaining 2 roots? The remaining 2 roots should also move towards infinity, but the remaining 2 roots are complex conjugate roots. So what you have to do first, you have to draw the angle of departure. Okay. So what is the angle of departure calculated at root A? It is 72 degree, -72 degrees. So what you have to do is, you have to keep your protractor, okay, in the downward direction, in the sense this direction. You have to keep your protractor, the angle measurement instrument, and then mark -72 degree line. So let's say somewhere here. Let's say I'll just do this somewhere here because the figure becomes very crowded. Say this is your point A. So what you have to do is you have to mark -72 degree line. Similarly, at point B, the angle of departure is +72 degree. So in quadrant 1, you are supposed to 72 degree. So this is what you have to do here. So this dotted line indicates that it's a -72 degree line, and somewhere here you will have a positive degree line. Okay. Now, as I mentioned in the beginning, while calculating phi d, at phi d, the root locus branch moves tangentially with respect to the phi d line. So tangentially means initially it should touch the phi d line. Like this it goes, and somewhere here you can give the deviation. Similarly, it goes like this, and somewhere here you can give the deviation. Okay. So it touched the 5D line tangentially, and then they move away. Move away where? Along the nearest asymptote. So where is the nearest asymptote? Theta 1 and theta 4. Now, when they move along the nearest asymptote, are they going to make any crossover with the j omega axis? Yes, they cross the j omega axis at minus 1.09 we have already found. So 1.09 is somewhere here, minus j 1.09, and this is plus, so this is plus j, this is minus j 1.09. So what you can do, you can just push the line somewhere here and just move it away. Similarly, this is your minus 1.2. Somewhere here, we move away. So everything needs to be done with respect to the asymptotes. This is your root locus. So you have predicted that all the 4 branches of the root locus move towards infinity. So this root move along with theta 1. This root move in the direction of theta 4. So as you vary the value of k, all 4 roots are moving towards infinity. And the point at which it makes the is your k margin. K margin. K margin. Okay. So k marginal is at 8.16. So the stability is something like this. If we operate the value of k between 0 and 8.16, all 4 roots will be in RHS of yes. Means to say all the 4 roots are found in left hand side of yes. On the other hand, at k equal to 8.16, the 2 roots are found on j omega axis, and that makes your system critically stable. On the other hand, any value of k which is greater than 8.16 makes the system unstable. Makes the system unstable. Okay. This is the root locus plot, and this is what you can conclude from the root locus plot. Breakaway point, they will break away with respect to the nearest asymptotes, because what is the definition of asymptote? Asymptotes are the guidelines for the branches of the root locus which are moving towards infinity. Similarly, these 2 roots, initially they move tangentially with respect to 5D line, and then they will cross over the j omega axis at the respective value, plus or minus j 1.09. And from then on, they move towards infinity in such a way that they are parallel to the nearest asymptotes. Okay. So that concludes the root locus problem. Okay. So please try to solve this problem, and I'm also scanning the note on root locus. Okay, I will forward it to you in some time. Please practice this problem using a graph sheet, and if you find any doubts or difficulties, please let me know.